In this recording, we're going to look at the nature of randomness and apply random events to a batting average on balls in play. To start with, I asked my students to flip in their minds a coin 100 times. So I gave them a sheet with 100 blanks and just asked them to flip a coin. And so they wrote down heads and tails. And then I had them use R to randomly flip 100 coins. So we simply use the sample function, and I'll set up a vector called samp. And we're going to sample either heads or tails. And we're going to flip our coin 100 times. And of course, I need to sample with replacement since I only have heads or tails to choose from. So we'll just run this line of code, and I'm going to convert it to a data frame to make the output easier to read, and we'll simply print the data frame to the console. What I did was to ask the students to give me 2 bits of information, both from their own generated heads and tails and from the R-generated heads and tail sequences. First, I asked for the number of runs. So anytime you switch from a tail to a head or vice versa, that ends and begins a run. So there's 1 run, 2, 3, 4, 3 tails in a row makes a 5th run, 3 heads in a row makes a 6th run. And I also asked them to go through and give me the longest run that they had. So there are 4 tails, and as we go through, 4 more tails there. There's a run of 5 tails, another run of 5 tails, and so forth. So I ask each student to do that, to give me the longest run of either heads or tails and how many different runs that they had. And what I did was to put it into a CSV file, and then I uploaded that. It's called flip here. So we can take a look at flip. So I simply have a factor variable here which says either computer or human, and these were the number of runs that were generated by each of those 100 coin flips, and the longest number of heads or tails is given there. So just to look at the other end of the data frame. So here we have human generated values down here. One thing we can do is to take a look to see if there's a difference in the number of runs that students generated versus the computer generated. One thing we can do is to ask if there is a statistically significant difference between the number of runs that the students generated with their own coin flipping and the runs that are generated. So we can just do a Ttest. So we're going to just test runs as a function of source, and the data is flip. And so we see that on average the R-generated coin flips had 51 runs, whereas the students had more runs, almost 60 runs. We can also look at what the length of the longest run would be. So we'll do the same sort of command here. So the longest run on average that the computer generated was 7 heads or tails in a row, whereas students it was 4, 4.5. Both of these differences are significantly different. As you can see, the p-values are very, very small for both of those t-tests. Might take a look at the data graphically. So we'll just call up ggplot. So we need these 2 packages that you can see at the top. So you need to load those if you're following along. So ggplot, we're going to use flip, and for my aesthetic, I'm going to have longest, and I'm going to subdivide my data by source, like so, and I'm just going to make a histogram. And so here you can see the difference between the two. The computer-generated data had longer runs. It was one run of 17 tails, as a matter of fact. And the students tended to have much shorter runs, 3, 4, 5, and 6. One student did have a run of 11. But the point here is that people often fail to realize that what appear to be streaks, either streaks of success or streaks of failure, may not be anything except random variation. That it's certainly possible to get, with a fair coin, 17 tails in a row or 13 tails in a row. People, I think, underestimate randomness as an explanation for what appear to be a pattern that might be caused by other factors. We can use this sort of approach to look at batting average on balls in play. So what we're going to be doing here is dealing only with batted balls that don't leave the ballpark. So any at-bat that results in a strikeout is not going to be useful for us, and any at-bat that produces a home run is not going to be useful for us because the fielders can't catch that ball. So essentially we're looking at what are the chances that a batted ball is going to be converted into an out. And we have some evidence that, in fact, that is random, that where balls are hit is primarily random, and whether they fall for a base hit or not is a random event. What we're going to be doing is looking at BABIP, batting average on balls in play, at the level of teams. So we're going to be using Sean Lehman's package. We'll be using the teams data frame. And what I'm going to do is to set up a separate object. So we're going to use the teams data frame, and I'm using the dplyr package. So we want to make sure that we require that. And I'll enter my piping operator here, and I only want relatively few of the columns in the team's data frame. I think there are 48 altogether. The ones we need are year ID, team ID, hits, home runs, at-bats, strikeouts, sacrifice flies. So we've got that. And I'm going to restrict my analysis to a single year. So we'll just do the most current year, current Lehman database, so 2014. Now, what I'm going to do is to issue some summarize commands, and to save a little time, I'm just going to paste those in, as you can see here. So here's what I've done. I have summarized for all of the teams in 2014. I've summarized all the hits, so I've got all the hits summed for all 30 teams. I have the sum of all the home runs. I have the sum of all the at-bats, all the strikeouts, and all the sacrifice flies. And now I can calculate BABIP. BABIP is calculated by taking the total number of hits minus the home runs. So these are all hits that stayed in the ballpark. And I'm going to divide that by the total number of at-bats minus those at-bats that produced a home run, minus those at-bats that produced a strikeout because the ball was not put in play, plus I'm going to add the number of sacrifice flies because the ball was put in play then, but it did not count as an at-bat. What I've done here is to round the number to 3 spaces to the right of the decimal point. So we'll run this code here, and BABIP is now a single number. It's essentially the summation of all of the team data collectively for 2014. So if I just run that, what I can get is the overall BABIP for 2014 in Major League Baseball, and it was almost at 300. And in fact, that is what we have discovered, is that BABIP is pretty close to 300. That seems to be the mean BABIP, and you can get variation above and below, but essentially the odds of a batted ball falling into spaces between fielders for a base hit is about 30%. Well, what we can do is to ask, well, what sort of variation is there among teams? So we'll simply add another line to our code here, and we're going to group by team ID. So I add my piping operator again here. Now I'll run all of this code, and I should get 30 lines of data this time instead of just one. So I have my 30 rows there, and let's just look at that up in the view window. So I've got all the 30 teams in 2014, and you can see that BABIP is roughly around 300, but occasionally, just because of randomness, even with this many at-bats, we get some deviation from that mean of 299. And as you can see, Colorado had a particularly high BABIP, and Detroit as well, so they may have been a little bit lucky that more of their balls fell into holes among the fielders than it was average. And on the other hand, you can see a team like Oakland had a relatively low BABIP. In an earlier video, we were doing the Pythagorean win expectations for 2014 Major League Baseball teams. And Oakland underperformed its expectation. Based on its runs and runs allowed, the Pythagorean win expectation was that they should have won 100 games. In fact, they only won 88. At least part of that explanation could be that they were just unlucky and that this low BABIP resulted in fewer wins than expected. If their BABIP were up around the Major League average of 300, they might have had a few more wins and had a closer agreement to their Pythagorean win expectation.